Look into the deep expanse of the Perseus galaxy cluster, and you'll find a massive volume of space that appears completely empty. In 2022, astronomers discovered that this void contained a hidden structure: four bright, tightly grouped spherical star clusters slowly drifting in orbit around an invisible center. They had found the galaxy CDG-2. Because the main body of the galaxy emitted no light, those four clusters acted as gravitational signposts. By tracking their orbital speeds, researchers calculated the immense invisible mass required to keep them tethered, pointing to a dark matter halo weighing roughly 1 billion solar masses. Curious, visualizing those estimates reveals a significant structural discrepancy. This block represents the proposed 1 billion solar mass halo, sitting next to a much smaller mass block representing the central core, which was calculated at just 200 million solar masses. Infrared and spectroscopic readings also picked up ambient temperatures of 10,000 to 30,000 Kelvin radiating from the center. This creates a problem for current models, as a galaxy dominated by dark matter should be cold and practically inert. Reconciling these two mathematical outliers, the missing mass and the unexpected heat, requires a model that can account for both, leading researchers to look beyond the dark matter paradigm. Starting at the outer edges of CDG-2, researcher Nathaniel Faxon-Sherrier proposed that the invisible halo surrounding the galaxy is composed of a massive cloud of neutrinos. Neutrinos are ghostly subatomic particles that flood the universe. They have a mass of only about 0.1 electron volts and travel at nearly the speed of light, interacting with the world almost exclusively through gravity and the weak nuclear force. This graph maps how a massive swarm of these particles would distribute around a gravity well. A peak density of 10 to the negative 4 particles per cubic centimeter creates a tapering curve that matches the exact visual gradient observed at the edges of CDG-2. Even a galaxy-sized cloud of neutrinos doesn't weigh much. This pie chart illustrates the scale. The entire neutrino halo equals roughly 1 billion solar masses, which covers only 1% of the galaxy's calculated weight. 99% remains unaccounted for. To hold those outer neutrino clouds and inner star clusters together, there must be an exceptionally dense, invisible anchor buried in the center. Traveling inward, past those four glowing globular clusters, we arrive at the coordinates where that immense gravitational pull originates. Sherrier's thesis suggests the gravitational source anchoring this system is a single ultra-dense point, a supermassive black hole. The required mass of this object is exactly 200 million solar masses, aligning with the original telescopic estimates for the galaxy's central core. It remains invisible because its accretion rate is near zero. It isn't actively pulling in and superheating surrounding gas and dust, meaning it emits no visible light. A dormant, non-feeding black hole of this size generates the precise gravitational strain needed to lock the star clusters into their current orbits without the need for dark matter. At the core of this system, we find the source of that inexplicable temperature reading. We are at the edge of a dormant black hole, yet telescopic data reads ambient temperatures up to 30,000 Kelvin. The mechanism at work here is Hawking radiation. Even without consuming matter, quantum effects at the edge of a black hole's event horizon cause it to slowly leak energy and heat out into space. There's a catch. A standard 200 million solar mass black hole has a very low baseline rate of Hawking radiation. On its own, it would not push the surrounding space to 10,000 Kelvin. But mapping the physics of this specific core shows a different result. This diagram illustrates a black hole carrying extreme rotational spin and a strong electromagnetic charge, which act as multipliers to amplify the outward pulse of radiation. This provides a mechanism for the 30,000 Kelvin heat, matching the thermal signature recorded by our telescopes. Stepping back from CDG-2, we can now see how this single galaxy fits into the broader cosmic web. The presence of a dormant central black hole suggests a history of aggressive star formation, followed by ancient supernovae that physically stripped away the galaxy's gas reserves. If an invisible mass discrepancy here can be solved by neutrinos and a black hole, the same mechanics might apply to other dark galaxies, challenging our reliance on dark matter dominance in galaxy formation. Verifying this requires the upcoming LISA observatory. This array of 3 spacecraft flying in a triangular formation is designed specifically to detect the gravitational waves a black hole of this scale would produce. Confirmation of those gravitational waves would prove that ordinary physics can explain the invisible mass of CDG-2. To keep exploring the universe with us, return to MDU and make sure to like and subscribe.